Hello everyone. So today we will be solving counting rooms problem from CSES. So in this problem, we have been given a map where dots are representing floors and hashes are representing walls. And in the input, we have been given the height and width of the map. And the question demands us to find out how many rooms are there. Now, the definition of a room is like the number of connected floors. Like from one of the floor we can move left, right, up and down, and as long as in the walk we are getting floors, then we will be connecting those floors, and uh, in the end, if we cannot uh, connect to another floor, then all those connection will designate a room. Cool. So here on the right I have made the picture. So here the hashes are the walls and the dots are the floor. Now the room, as per the definition, rooms are like this. Let's say I start from this floor. I will connect this. Okay, like I will walk from here to here. Okay, so I got a floor. Now from here I cannot move to any other direction because all these are walls. So I will say this segment as a room. Cool. Now same story here. Like uh, we have a floor here, then from this we cannot move to any other direction except on the right. So this part is a room. Now here the story is little different. Like let's say I start from this, I go here, then I go here, then I go here, I go here. So like this I will be moving. So you can see like inside this we have a wall, but all these floors are connected. So that's why this will be considered as a room. So here we have the number of rooms as 3. Now, so the answer to the question is simply like uh, if we can count the number of connected floors, then we can give the count of the number of rooms. So number of connected floors is equal to our number of rooms. Now, in order to solve this problem, we can use either a DFS approach or a BFS approach. Now, the approach is pretty simple. So we just have to imagine all these floors, uh, all these walls and the floors as components. So they will look something like this. Like you have your walls like here, and inside that we have some rooms, something like this. Like these are the nodes. Okay. So the walls are connected to each other, something like this. Okay. And if we are able to figure out how many connected floors are there, okay, then we should be able to answer. Cool. Cool. Now we can start the coding. So I'll be declaring the graph as a global variable so that we can use it in our DFS call. Like no need to supply it as another argument to our DFS. Then instead of height and width, I will be using rows and columns. And yeah, so I will be coding in DFS, but feel free to do it in BFS, like both works. So, okay, now we are done with this. Now let's take the input first. So we have been given the height, that will be my rows, and next the width, that's the number of columns. Cool. Now after this we have been given this graph, so I can resize my graph as per the height or the rows. Now let's quickly take the input. Okay, now I'll be calling the DFS. So it will be something like for 0 less call call. Now whenever so I will be iterating over each cell in the matrix, and whenever I'm getting a floor which will be designated as like this, then I will call my DFS, and I will also initialize my answer. So rooms 0. Cool. And let's call the DFS here. So far I haven't coded my DFS code, but yeah, we'll be doing that shortly. So yeah, I will be incrementing the rooms. And in the end, I will be returning that, not returning, printing. Now let's quickly complete our DFS. So our DFS take the position or the coordinate of the room. Now in standard DFS and BFS, we need another matrix or array to figure out whichever cells we have already visited. But we don't need that. We can use the same graph and mark all the visited cell with wall representation. That will reduce our space complexity. So first of all, let's do the coordinate check. So if row is less than 0 or call is less than 0, and if row has become equal to the total number of rows, or call has become equal to the total number of columns, or we have hit a wall, then I will simply return from that. Let me zoom it out. Or not the DFS, or yeah, it should be something like, yeah, so graph of row call equal to a hash. That means it's a wall, so we cannot proceed, right? Now if everything is good, we have a floor, then I will mark that as I will mark that visited by representing it as a wall, and then I will be iterating over its neighboring cells. Now you can like code like brute forcely, but like for every direction you can change the coordinates and call the DFS with that. But to keep it simple and you can say pretty, we can use a direction vector. So it looks something like this: -1 0 1 0 -1. Now what it basically does is, so let me first complete it, then I will uh, then I will explain. For so here I will be doing new row dir that will be row plus dirs of I, and new call will become call plus dirs of I plus 1, and then I will be calling my DFS with the new row and new call. Cool. So what we are basically doing is we are taking pairs of the elements in this direction vector. So the first pair basically designate that. So I will be doing a -1 to the row. That means I'm moving up, like I'm doing row -1, and I will be adding 0 to the call. So I'm not moving in the horizontal direction. I'm only moving up in the vertical direction, right? So this symbolizes like I'm going up. Now in the second iteration of this for loop, like when I becomes 1, so I will be here and the adjacent partner will be 1. So here if you look, so I will be doing 0 addition to the row. So we are not moving in the vertical direction, but on the call side, I'll be adding a 1. So that basically means I'm incrementing my call. So that's a right movement, right? Then likewise, this will designate down movement and this will designate left movement. So yeah, so this for loop and this direction vector are pretty kind of standard things, because these kind of direction vector helps you to like reduce down the code. Otherwise I would have to do like a row minus 1 call plus 0. So in order to reduce all that writings, we can simply use this and call a for loop, and it will move all the, so it will move around basically like in all four direction. Cool. Now let's quickly take this input and fingers crossed. Let's see if everything works. Cool, everything works. So we got 3 here. Now I can make a submit. And it would have been very cool like if you can paste your code directly here. Yeah, it's main.cpp and I hit submit. Cool, all got accepted. So if we see the time complexity here, so you can check like, so you might ask like, hey, we have a for loop here, then we are calling a DFS here, won't it be like TLE? No, because here we are moving around every cell, that we agree, but I'm only calling on the DFS whenever I'm hitting a floor, right? Now when I'm hitting a floor, I'm calling my DFS and I'm moving around all the possible position, like all the possible neighboring floors for that current iteration, right? And whichever I am done visited, then I'm marking with the marking it with a hash, like I'm making them a wall. So even if in this two, like in this nested iteration, I'm getting another coordinate which I have already got in some previous DFS call, I will not be doing that, because that won't be a dot, that will be converted into a wall. So yeah, with that, the number of calls we are reducing. So the time complexity here will be the number of floors that we have. Okay, because for every cell we are not, like for every cell which is a wall, we are not doing any operation, we are just iterating over them and quickly skipping them. But for floor operation we are calling DFS with it. So here the time complexity will be big O of number of floors that we have. So yeah, so number of floors you can consider, like if we have n times n floor, let's say all the floors are there, like all the elements in this matrices matrix are floors, then we will be doing a big O of like row times uh, call operations. So yeah, that will be the time complexity here. And as per space complexity, since we are not using any extra space, and like no data structure is like growing linearly or exponentially, we have like static data structures like diars, like its length is 5, that is constant. And for graph we are taking just input, so whenever we are doing a space complexity calculation, we do not consider the inputs as our space complexity. Whenever we are using another data structure for processing, then only we consider the space complexity. So auxiliary space complexity, to be more precise, is big O of 1. So yeah, so we have solved this problem, and I hope you learned something new today. Just stay tuned to watch more videos on CSES.